Today, we're diving into lithium cobalt oxide, or LCO, the key material that powers your phone, laptop, and countless portable devices. You might not think about it, but every time you charge your battery, lithium ions are on the move, storing and releasing energy in a perfectly controlled dance. But here's the catch. LCO is great for small electronics, yet it's nowhere to be found in electric vehicles. Why? What makes it perfect for your phone but useless for your car? And what's happening at the atomic level that determines its fate? Stick around for a deep dive into the chemistry behind one of the most important battery materials. Now let's dive deep into the chemistry of lithium cobalt oxide, or LCO, the material at the heart of many lithium-ion batteries. If we zoom in at the atomic level, what do we actually see? Imagine walking into a grand Gothic cathedral. The towering stone columns stretch toward the vaulted ceiling, holding up the entire structure. These columns represent the cobalt oxygen layers, COO2, strong, rigid, and essential for stability. But between them, there are open spaces, just like the gaps between the columns, and this is where lithium ions sit, ready to move in and out as the battery charges and discharges. LCO has a layered crystal structure, meaning it's built in thin atomic sheets stacked like a bookshelf. The cobalt oxygen layers act as the shelves, and lithium ions sit neatly in between until they're pulled out during charging. More specifically, cobalt atoms are surrounded by 6 oxygen atoms in an octahedral coordination, forming cobalt-oxygen 6 units. These COO6 octahedra are interconnected, creating a strong, two-dimensional layered framework. The lithium ions are intercalated between these layers, meaning they can be reversibly inserted and removed as the battery charges and discharges. When we charge the battery, lithium ions are extracted from these interlayer spaces and migrate toward the anode. This is like removing books from a shelf. The structure stays intact, but if too many are removed at once, the stability of the framework is at risk. When you discharge the battery, lithium returns, restoring balance, just like placing the books back in their slots. Now, why do we need cobalt? Why not another metal? Cobalt plays 2 critical roles in lithium cobalt oxide. First, structural stability. Imagine if we replaced the cathedral's stone columns with weaker wooden beams. Over time, the structure would crack and collapse. Cobalt ensures that the cobalt oxide layers remain stable, even as lithium moves in and out. The strong cobalt-oxygen bonds help maintain the integrity of the crystal lattice, preventing unwanted degradation and structural failure. Second, electronic conductivity. Think of a highway system, where cars represent electrons. Cobalt acts like reinforced steel bridges, ensuring electrons flow efficiently and preventing bottlenecks in the system. Specifically, the cobalt 3+ to cobalt 4+ redox transitions enable fast electron transport, allowing lithium cobalt oxide to maintain high conductivity, which is essential for efficient battery performance. Now that we've covered the structure of LCO, let's explore the chemistry behind how it stores and releases energy. This all comes down to the movement of lithium ions and electrons, which take part in a series of reversible reactions that make this material rechargeable. So what actually happens when we charge and discharge the battery? Let's start with charging. When we plug in the battery, lithium ions are pulled out of the material and moved toward the anode. This changes the structure from lithium cobalt oxide to lithium-1-X cobalt oxide, meaning that some of the lithium has been removed. But lithium ions don't just disappear. They leave behind an imbalance. To compensate, cobalt atoms lose electrons, shifting from cobalt 3+ to cobalt 4+. You can think of this like a hotel manager who suddenly has to handle more responsibilities because many guests' lithium ions have checked out. At the same time, these electrons flow through the external circuit, providing the energy needed to charge the battery. Now, when we discharge, that is, when we actually use the battery, the process reverses. The lithium ions return from the anode and reinsert themselves between the cobalt-oxygen 2 layers, just like books being placed back on the shelf. Meanwhile, electrons that previously left the structure now flow back, reducing cobalt from cobalt 4+ to cobalt 3+, restoring the original material lithium cobalt oxide. The hotel manager can finally relax as the guests come back, and the structure is once again balanced. This constant back-and-forth movement of lithium ions and electrons, known as redox cycling, is what makes lithium-ion batteries rechargeable. As long as the structure remains stable, this process can repeat hundreds or even thousands of times, providing a long-lasting energy storage solution. But here's the catch. If too many lithium ions are removed, or if the structure weakens over time, the battery begins to degrade. And this is part of the reason why LCO, despite being highly effective for small electronics, isn't the best choice for electric vehicles. So now that we understand how LCO stores and releases energy, let's explore how it's actually made. To produce lithium cobalt oxide, we start with lithium and cobalt compounds. The lithium source is typically lithium carbonate or lithium hydroxide, while the cobalt source is usually cobalt oxide or cobalt hydroxide. These raw materials provide the essential elements, lithium, cobalt, and oxygen, that form the final crystal structure of LCO. One of the biggest challenges in making high-quality LCO is ensuring lithium is evenly spread throughout the particles. If lithium clusters in some regions while leaving others deficient, the battery's performance suffers, leading to inconsistent capacity and shorter lifespan. To prevent this, manufacturers carefully control the mixing process before heating the material. Using precursors with very fine particle sizes helps lithium react uniformly with cobalt across the entire structure. During heating, a slow, controlled temperature increase allows lithium to diffuse deep inside each particle rather than accumulating on the surface. Think of it like baking a cake. If the ingredients aren't mixed properly, you end up with flour pockets instead of a smooth texture. When properly synthesized, LCO has a homogeneous structure, ensuring that every part of the material can store and release lithium efficiently, maximizing energy storage and battery life. The first step is to thoroughly mix and grind these powders, ensuring that lithium is evenly distributed among the cobalt and oxygen atoms. However, at this stage, the layered structure needed for a functional cathode hasn't formed yet. To achieve this, the mixture is heated to around 800 degrees Celsius in an oxygen-rich atmosphere, a process known as solid-state synthesis. If we use lithium carbonate and cobalt-3 oxide 4 as the starting materials, the reaction begins when lithium carbonate decomposes under heat, releasing carbon dioxide gas and leaving behind lithium oxide. This lithium oxide then reacts with cobalt-3 oxide 4 in the presence of oxygen, forming the final layered structure of lithium cobalt oxide. This step is crucial, as it gives LCO its organized atomic arrangement, allowing lithium ions to move in and out efficiently. If we use lithium hydroxide instead of lithium carbonate, the reaction is slightly different. Instead of releasing carbon dioxide, lithium hydroxide gives off water vapor as it transforms into lithium cobalt oxide. Regardless of the lithium source, this high-temperature reaction forces the atoms to rearrange themselves, forming LCO's layered crystal structure. Lithium ions become positioned between the cobalt-oxygen layers, creating a stable and rechargeable cathode material. This precise atomic arrangement allows smooth lithium-ion migration, enabling efficient energy storage and release in a battery. Once LCO is formed, it acts as a host material for lithium ions. These lithium plus ions don't just sit still. They move in and out of the layers as the battery is charged and discharged. Lithium migrates through specific pathways inside the crystal structure, moving between the cobalt oxide layers without disturbing the overall framework. However, this migration can only happen efficiently if the layers remain well aligned and do not collapse over time. If lithium is unevenly distributed, certain regions of the material may become lithium deficient, leading to structural instability and faster battery degradation. That's why perfecting the synthesis process is critical to ensuring long battery life. While lithium cobalt oxide works well, it has limitations, especially in cycle life and stability. Over time, repeated charging and discharging cause the cobalt-oxygen layers to shift or degrade, leading to capacity loss. To improve durability, manufacturers use two key strategies: doping and coating. Doping extends LCO's lifespan by introducing small amounts of other metal ions into the structure. This reinforces the cobalt-oxygen layers, making them less prone to collapse or unwanted reactions. Think of it like adding steel reinforcements to a stone bridge. The overall structure remains the same, but becomes stronger and more resistant to wear. Different dopants provide specific benefits. Magnesium 2 plus prevents structural collapse by reducing strain from lithium-ion movement, preventing cracks and prolonging battery life. Aluminum 3 plus enhances thermal stability, reducing the risk of oxygen release and thermal runaway by making the structure more heat resistant. Nickel 2 plus slightly increases energy density while maintaining good cycle life, helping boost capacity without compromising long-term stability. Doping has become a standard technique in LCO manufacturing, improving battery lifespan and safety. However, while doping strengthens the internal structure, LCO's surface also needs protection, which is where coatings come in. LCO is in direct contact with the liquid electrolyte, and over time, unwanted side reactions at the surface can form a thin, resistive film, slowing down lithium-ion movement and reducing performance. To prevent this, manufacturers apply ultra-thin protective coatings that shield LCO from electrolyte exposure while still allowing lithium ions to move freely. Aluminum oxide forms a stable surface barrier, preventing electrolyte degradation and extending battery life. Titanium dioxide blocks unwanted side reactions while allowing lithium ions to move efficiently. A good analogy is the glaze on a ceramic pot. It doesn't change the fundamental structure, but protects the surface from damage. Similarly, coatings preserve LCO's integrity, ensuring it functions smoothly and efficiently inside the battery. So far, we've explored the chemistry of lithium cobalt oxide, how it works, and how it's made. But while LCO has been a game changer for portable electronics, it's almost never used in electric vehicles. Why? The main reasons come down to safety, lifespan, and cost, and the biggest risk of all is something hidden deep in its chemistry: the release of oxygen at high voltages. To understand why lithium cobalt oxide becomes unstable at high voltages, we need to examine how cobalt-oxygen bonds behave during charge and discharge. When a battery is fully charged, most of the lithium ions in LCO have been removed from the structure. This forces cobalt, which normally exists in the +3 oxidation state, to remain in the highly oxidized +4 state. The problem is, this state is not particularly stable, and at voltages above 4.4 volts, the entire structure begins to break down. The cobalt-oxygen layers in LCO are held together by a delicate balance of chemical bonding interactions between cobalt and oxygen. Specifically, oxygen's 2p orbitals overlap with cobalt's 3d orbitals, forming strong covalent bonds that help maintain structural stability, but only as long as there are enough lithium ions present to balance the charge. When lithium is removed, cobalt is forced to take on more of the electronic burden. At very high charge levels, these cobalt-oxygen bonds weaken, and oxygen can no longer remain stably bonded within the lattice. At this point, oxygen atoms begin to escape from the structure as oxygen gas. Free oxygen is highly reactive in a lithium-ion battery environment. If enough oxygen is released, it reacts with the electrolyte, triggering exothermic reactions, heat-releasing processes that accelerate further decomposition. This creates a self-sustaining chain reaction known as thermal runaway, where the battery temperature rapidly increases, potentially leading to fire or explosion. Imagine a skyscraper where steel supports are slowly being removed. At first, the building might hold up, but eventually it reaches a tipping point where the entire structure collapses catastrophically. That's exactly what happens in LCO at very high voltages. Except instead of a collapsing building, you have a battery that overheats and breaks down uncontrollably. Because of this fundamental instability, lithium cobalt oxide cannot be safely used in electric vehicles, where batteries regularly cycle through high voltages and store large amounts of energy. Instead, safer, more stable cathode materials like nickel manganese cobalt oxide or nickel cobalty aluminum oxide have replaced LCO in EV applications. Beyond safety concerns, LCO also has a relatively short cycle life, meaning it wears out faster than other cathode materials. As we discussed earlier, charging and discharging cause lithium ions to move in and out of the structure. Over time, this mechanical expansion and contraction can lead to microcracks forming inside the material. These cracks reduce conductivity, make it harder for lithium to diffuse, and eventually cause the battery to lose capacity. For a smartphone battery, this degradation might take a few years to become noticeable, but for an electric vehicle, where a battery is expected to last hundreds of thousands of kilometers, this would be a major issue. Automakers need batteries that last thousands of charge cycles, something LCO simply cannot offer. Beyond safety and cost, lithium cobalt oxide simply doesn't provide the energy density and power capability that electric vehicles require. Think of LCO as a city scooter and NMC-NCA as a touring motorcycle. A scooter is efficient for short trips, perfect for navigating compact urban spaces, but it lacks the range and power for long-distance travel. In contrast, a touring motorcycle is built for extended journeys with higher energy storage and sustained performance, exactly what an EV battery needs. Lower energy density. LCO has a lower energy capacity per kilogram than high nickel cathodes like nickel manganese cobalt, NMC, and nickel cobalt aluminum, NCA. This means that for the same battery weight, an EV using LCO would have a significantly shorter driving range compared to one using newer cathode chemistries. Poorer rate capability. LCO struggles to deliver high power output efficiently, making it unsuitable for rapid acceleration or fast charging, two critical demands for electric vehicle batteries. Because of these safety, lifespan, cost, and performance limitations, LCO has remained the preferred choice for small electronics, but has been completely phased out of EVs in favor of safer, higher energy cathode materials. So while LCO revolutionized portable electronics, its instability at high voltages, short lifespan, and supply chain challenges make it unsuitable for electric vehicles. Even if LCO were stable, there's another major obstacle to using it in EVs. Cobalt is expensive, and its supply chain is problematic. Cobalt mining is concentrated in just a few locations, particularly the Democratic Republic of Congo, where over 70% of the world's cobalt supply is produced. However, mining conditions there have raised serious concerns about human rights violations, child labor, and environmental destruction. Because of these ethical and geopolitical issues, the battery industry has been actively reducing cobalt content in favor of alternative cathodes that use less, or even zero, cobalt. I hope you enjoyed this deep dive into lithium cobalt oxide. If you found this interesting, make sure to like, subscribe, and hit the notification bell so you don't miss future deep dives into the chemistry of materials. And if you have questions, thoughts, or ideas for future episodes, drop a comment below or reach out. I'd love to hear from you. Thanks for listening, and see you next time.